Well, welcome back, everyone. Looks like we have less than a minute. We'll run the clock and get started shortly. Well, I think we can start. Welcome back, everyone. So today's class, we're doing our last example in section 4.1 on maximum minimum values. And the last two examples really are pretty much what quiz 7 is all about, the closed interval method, which means you can probably pretty much expect that's going to be on exam 3, probably on the final exam as well. After we finish that off, we'll get back into section 4.2 next on just more information about the derivative. 4.2 is one of the more pivotal sections of chapter 4 because that's the one section that's going to allow us to do the optimization problems, which is the big application to differential calculus. So that's where we're at so far, folks. Quiz 6 is due today, but if you need a little extra time on that, no worries. I can take those late. And again, quiz 7 is heavily based on section 4.1. Well, any questions at all, folks, before we get started with today's work? Okay, well, let's jump in. Section 4.1. I've got the last problem that we finished up, just loaded in. So the idea with the closed interval method is its whole purpose, this method right here, is to find the absolute maximum and absolute minimum. So that's what makes this method really special. We'll see in section 4.2, our methods are just giving local maxes, local minimums. So this is the one that gives us the absolute max and min. The process isn't too bad. Virtually every time you're doing something in chapter 4, it always starts right here, like we mentioned. Find the critical numbers of f in the set. But what that's really saying to do in step 1 is this. Solve f prime of x equals 0. That's really the heart of the method. Once you find these solutions here for x, then step 2, you just evaluate the original function f, not the derivative, the function f, at the endpoints of the interval. When it says endpoints of the interval, we're referring to the a and the b in the closed interval provided. In this problem, the endpoints were 1/2 and 2 over here. Then we also evaluate at the critical numbers we got in step 1, and that's what we did on the work here. So let's take a look. For part A, we had x minus natural log x. We formed the derivative here, set it to 0, so now we're hunting for the critical numbers. And this method looks like we added 1 over x to both sides, and then just multiplied both sides by x. So that was our critical number. But then next we had to grab those two values, the endpoints, the critical number, and note we just evaluate the function at those specific points. Once we did all that, we found that the maximum, we needed a calculator to really see if it was a maximum. These are tricky numbers with the natural log. But after estimating the calculator, we saw that the maximum occurs at f of 2. The actual maximum has to be written as an exact number, so we wrote 2 natural log 2 is the absolute max. And then the smallest number in the list, that's the absolute minimum. It comes out as 1 just because this one simplifies. So that's the whole process. Once you get some practice on this, doing it a few times in the homework, do it again as a quiz, it's not so bad. Let me just see if I can reset this highlighting. That is way harder than it looks. Let me just Control Z it off. Oh yeah, Control Z doesn't actually work on this computer too well all the time either. But any questions at all, folks, on running through that review problem here? Okay, well, let's try it again for real on part B. I would say part A here is a pretty standard problem if it was in an exam setting. This one is a little bit tougher. This could be an exam problem, but I'd have to shorten the exam just to make room for the length of this one. The only reason this is a longer problem is just because the derivative is a little bit trickier. Same idea, we want to find the absolute maximum, absolute minimum. So step 1, let's still write out the steps, is to begin this way. we need to calculate f prime of x. But it is a trickier derivative, so this is kind of a review in its own right. Analyzing the form of the function, we have x multiplying e to the negative x squared over 8. So that's kind of a lot of stuff. That means we have one factor here multiplying the other factor, and this is now a product rule problem. So this will turn into, first we'll differentiate x, copy the exponential, e negative x squared over 8. In the product rule, we put plus in the middle, copy the first factor x, and then differentiate the second factor, e to the negative x squared over 2 prime. So now we've got the product rule set up. Derivative over here, not so bad. I'll do that one. That derivative comes out as a 1, so we're done. This derivative is like a problem in its own right. This requires the chain rule, so we'll take our time on that one. So looking at the form of the function, the inner function is the thing going inside the exponential. The exponential originally looks like this, e to the x. In place of x, we've got an entire negative x squared divided by 2. So all of this right here, the inner function. Sorry, your open mic, let me just close those. Then over here, the base c exponential, this is function 1, the outer. Well, any questions, folks, with the setup here, getting ready to go with the chain rule? Oh, that's too far, there we go. Okay, let's proceed through the next steps. So here's f prime of x. At the moment, it's now equal to derivative of x. We get just a 1. Putting the 1 there just as a kind of paper trail saying we did calculate e negative x squared over 8. Then plus, actually, let me drop this slightly lower so we're not cramming things in. Derivative of x is 1, just copying again, times e to the negative x squared over 8 plus x. And then finally, here's where it gets interesting. We differentiate the outer function. That's the base e exponential. But notice every time we do the chain rule, where there would have been an x, we just put a big placeholder, a set of parentheses. So we multiply by the derivative of whatever goes in that placeholder. And the thing going inside both of these placeholders now is the inner function. So that's our pattern each and every time. But as the functions change, the pattern just feels different. It's always good to kind of reinforce the process. So inner function, negative x squared over 2, will go here. We'll drop those parentheses on the next step. And it also goes here. Let's write to negative x squared over 2 this way. Negative 1/2 x squared. Jamie says it's over 8. Oh, thanks for catching that. I don't know how I got from a 8 to a 2. Thanks for spotting it. Let's put in the correction here. And here. And here. Good catch. That sometimes when you catch them slightly late, those mistakes just spread out. So negative x squared over 8. 8. And 8. Thanks again, Jamie. Other questions at the moment? Okay. Now, one thing that's kind of interesting about this is, notice this slight change of point of view we took. This is an ordinary fraction written sideways, but if you're going to differentiate it, you probably want to pull out the constant. Negative x squared divided by 8 is just the same as negative 1/8 times x squared. But in this format, it's just easier to visualize that derivative. So we're still calculating f prime of x. We're following down the equalities. So the next line, still f prime of x. We have e negative x squared over 8 plus x times, I'll put this one in black since we're not doing anything with it. That portion's done. E to the negative x squared over 8 again. Then we differentiate this one. We need a parenthesis so we can express that this is multiplying, not subtracting something. It's negative 1/8 multiplied by derivative of x squared. That's a 2x. And at this stage, it's all algebra from here. We've cleared out all the derivatives. Any questions at all, folks, on navigating through this process here? Okay, so let's start simplifying this as much as feasibly possible. We definitely want to simplify what's going on here in green, but another thing we can do is, because we're solving an equation, we need to set the derivative equal to 0 and solve in step 1. We should start factoring as well. Let's factor out e negative x squared over 8 because it appears in both terms here and here. So it turns into this, e negative x squared over 8. In place of where it was by the red dot, there's just a 1 now. Plus, over here it's just an x. From here, we're going to simplify this just a little bit more. That's now negative 1/4 of x. And a little bit more simplification here, and we'll have our derivative in its most simplified form. So here's our next step. E negative x squared over 8, 1 minus 1/4 x squared. So all I've done in this next step is just drop these parentheses, convert it to subtraction, and take x times x, forming that x squared. At this stage, recall in step 1, we're trying to find the critical number. So we're ready to solve the derivative set equal to 0. Recall in step 1, our goal is to do this. Solve f prime of x equals 0. So that's why we started with f prime of x here, and we started simplifying it all the way down to this point. Here, we're setting it equal to 0, and we're ready to solve. The reason we took the factoring step is we can now use a zero product property of real numbers. We have two different things multiplying each other, this portion and this portion. But in the real number system, the only way two things multiply and result in a 0 is if the first factor was 0. So we can say that equation implies e negative x squared over 8 is 0, or the culprit could have been the second factor was 0. So 1 minus 1/4 x squared equals 0. So we had one tough equation here, but because we factored it, it splits into two slightly nicer equations to solve. Now, this one is a tricky one. Anytime you get an exponential, we have this nice idea here. E to the power of a, think of a as a way to say anything whatsoever. It's always positive no matter what. And it doesn't hurt to visualize that a little bit better. Let's write out y equals e to the x. So definitely it always looks positive. Looks suspicious out here on the left end. But as you click here, you'll notice first coordinate is x, second coordinate says 0. That would be a lie. Let's see if we can zoom in and show that it's really positive. Could take a moment. This is an exponential function after all. We're getting there, I promise. So after loads and loads of zooming, you can see that, well, I'm not quite at negative 15 anymore. I kind of left that spot after zooming. But the second coordinate is positive. Sure, it just has times 10 to the power negative 7. So it's positive, but very, very close to 0. I agree, that's kind of strange with these kinds of functions. The exponential approaches the x-axis extremely fast, but this equation says it never actually hits the x-axis. It's always positive. But that then in turn means over here, if you have an exponential function set to 0, this is automatically no solution. It doesn't mean we have no solutions to this, the derivative set equal to 0. It just means on that factor right there, no solutions can be gotten. So we just convert over to the second factor and solve that one. Any questions so far, folks, on handling that first factor before we move on to the next? Okay, lots of ways to solve the second equation here by the red dot. I think, again, probably the easiest way is just to add 1/4 x squared to both sides. So we have 1 equals 1/4 x squared. Next, a good call here is just clear denominators. Multiply both sides by 4. So 4 is now equal to x squared. Next thing we have to watch out for, however, is if we take the square root of both sides of this equation, there are two potential solutions, either a positive or a negative. So we'll have plus or minus the root of 4 equals x. So we're now ready to say that this implies x equals -2 or +2. Think of the comma as literally saying or. So -2 came from the negative root, positive came from the positive root. But as we're staring at that, those are not both guaranteed to be the critical numbers. There's a bigger context going on with the function, so let's hold this thought for just a moment. Grab the original part of the problem. It's kind of unfortunate these get so long that we scroll so much. And I just want to park that somewhere in view. There we go. So here's our function. But remember, functions come with two components. A way to evaluate and get an output for a given x. That's this portion right here. But it also comes with a domain. Our domain is the closed interval from -1 to 4, which tells us -2 is out of here. We have to eliminate it. Let's put a quick note since that is tricky. -2 is not in -1, 4, the given domain of the function. So finally we get to say, therefore, x equals 2 is the critical number. I'll often use hash for a shorthand for number. So we did it, folks. That's step 1. That's really the meat of the process. Most of the credit can come right at step 1 because of all the steps we have to take. Steps 2 and 3 is just summarizing what we found. Any questions or comments at this point, folks? Okay, let's go off then to step number 2. Slide scroll. So for step 2, this is what we're doing. We go to the closed interval and we're only looking at the boundary values, -1 and 4. We also take a look at the critical number and we need to evaluate the function f. It's a good idea to always write things like this f prime right here, so you know you're looking at your derivative as you go down. And start by writing f on this step, because it's a huge reminder you're not using the derivative in step 2. You're using the original function. The logic is you're trying to find the maximums and minimums of the original function. And so at some point we have to actually use this again. So take f, evaluate it at -1, evaluate it at 2, and evaluate it at 4. I usually like to go in order, so that's just a me thing. You don't have to. You can do these in any one kind of order. I started at -1, the left end of the boundary, put in the critical 2, so there's f of 2 here, and then ended with f at 4, the right end of the boundary. Now we just have to calculate all 3 of these and see what we get. Here's what it would look like. F at -1, placing a -1 here, so it's negative e to the power. -1 where there's an x squared is just going to turn this into a -1 squared for a +1. But then there's another negative right in front. So it's -1/8. Plugging in the 2 is not as bad. We'll get 2 e to the power of negative, by the red dot when we plug in a 2, that's 4. So it's -4/8. We might as well simplify that one. That's 2 e to the power of -1/2. One more time, plug in 4. You first get a 4 here. E to the power of 4 gets squared right here, then it gets negated. So it's -16 divided by 8. So we get 4 e to the power of -2. So these are all the function evaluations. And in step 3, it says the largest value here is the absolute maximum, and the smallest value here is the absolute minimum. But if you're like me, I can't tell you what the largest or smallest are just yet. We need to actually approximate these to get a good feel. So that's where this problem becomes a calculator problem. Pull up our good old trusty calculator. Let's do the three evaluations. So negative e power -1 divided by 8. But that's 9. Let me try again, 8. So first one, let's keep 3 decimals in case these numbers are close to each other. It's negative 0.882. So approximately negative 0.882. Then let's do it again. Next one is going to have negative 1/2, but it's also a positive 2 right out in front. So we're looking at 1.213. And last one, we throw a 4 out in front. This turns into a -2. And that one came out as a 0.541. So now we know which one is the maximum value. It's going to be this one right here. The minimum is going to be, well, I'll almost grab that one, but this has a negative sign, so it has to be this one. So for step 3, we're ready to give a conclusion. Really not much to say. We're just sort of reiterating what we see right here. We'll say, let's start with this one, the maximum. The absolute max is 2e to the power -1/2. And the absolute min is -e -power 1/8. So that finally solves the problem. We're grabbing the exact values since we have them. But if it were, say, a quiz or exam, I'm not too opposed if you just gave me the approximation. I'm not too big of a stickler on that. But watch out for WebAssign. Oftentimes they do want the exact values like I've been highlighting here. And that's why we've been focusing on them in the notes. But we did, folks. We have found the absolute max, absolute min of this function. It's those two values and the approximations here in case we needed them. Any questions at all with running through that full process? Okay, well, we did it, folks. That's our entry section 4.1 on applications of the derivative. So already we have interesting applications. It can help us maximize and minimize something. This is one of our premier methods if you're looking for an absolute max or absolute min. And just to make it clear on the notes, where we wrote ABS dot, we're saying absolute. But now let's switch gears. Let me save this just so we don't lose anything. And we're going to go over to section 4.2 next. This one is a bigger section, so definitely not planning to finish it today. We'll probably finish it about midway in Monday's class when we come back next week. It's about how derivatives affect the shape of a graph. And so when you open up those notes, there's a bunch of review information because the things we were doing in chapter 3, talking about the derivative, is extremely relevant now to these notes here, section 4.2. So here's our reminder. If f is a function, the derivative is just a form of limit. It's written in this way, kind of a beast to calculate, so that's why in chapter 3 we have all those differentiation formulas to help us out. This could come back as a final exam question to do it one more time, like you saw in exam 2. But the whole purpose of those equations is just a reminder, this is what the derivative really is. But it also has a geometric interpretation. If that limit right here exists, then its value, f prime of x, is the slope of the tangent line. And that gives us a lot of really important information. Let's maybe pause right here with this thought and go back to a prior section. Let's see, good section might be 3.2, I'd say. This ought to do the job. At section 3.2, we were using the same ideas. We were looking into the derivative being equal to the slope of the tangent line. And so we have this function right here, y equals f of x. And we used nothing but the graph of this function to plot the derivative right down below it. So let's take this as a big screenshot. I guess we want the part that says y equals f prime of x as well. Let's just dump it in the notes. Okay, so with this here in context, here's what the increasing decreasing test is trying to say altogether. Because the derivative is the slope of the tangent line, we put a dot somewhere, like right here where the red dot is. Slope of the tangent line is now negative, and that's why down below here, we have the curve below the axis. But it's also saying if your derivative is negative, your function f is decreasing. That's pretty clear to see. It's a negative slope anywhere you put tangent line here, and the curve is also decreasing at the same time. When we get here, we're at a horizontal tangent line. The derivative is 0, in other words, so that matches up with the dot down here. As we go into this region, well, the derivative is now positive because the slope of the tangent line over here, let's actually draw this one in. Anywhere we put a tangent line, say over here, its slope looks like this, and bigger than 0. This means the derivative is bigger than 0 here. And that's why if we go where the red dot is and go directly to here, that's why we plotted with the derivative above the x-axis in this one spot. But here's where it's saying once and for all, if your derivative f is positive, that's what we have right here, then your function is increasing on that interval. And that's what we see, increasing with a positive derivative. So that's a big rundown of the increasing, decreasing test. What we're going to do with this is, this leads to optimization. Because you notice where the derivative is negative here, and then it comes out to 0, that's where a critical number exists, and comes up positive, that tells you where a local minimum would be. Likewise, if your derivative is positive, it's increasing, and then you hit a critical number of 0 derivative, horizontal tangent line, and then goes to decreasing, well, that must have meant there's a local maximum. Putting all those observations into one little spot gives us this test finally. The first derivative test. Here's just a reminder in the notes, so everything is in one spot. You don't have to dig these things out in a different section. We need a critical number to make this all happen. And the reason we need critical numbers is, notice, that's where we're going to find a local minimum, local maximum, and another local minimum. A critical number is where the derivative is 0 or doesn't exist. So the first derivative test now says, find your critical numbers of the function. Then the derivative changes from positive to negative at c, then you have a local maximum. If the derivative changes from negative to positive at c, you have a local minimum instead. And if the sign doesn't change, then f of c is neither a local maximum nor a local minimum. Well, any questions with first derivative test at the moment? Okay, well, let's try it out right away. Here's our function f of x. It's a degree 3 polynomial. We want to find the intervals where f is increasing and where it's decreasing. And usually there's a bigger takeaway. We're more interested in the local minimum and local maximum values of f. So part B is like the summary. Almost all of your work is over here in part A. So here's how it starts. We begin by finding your critical number, which it means we're doing the same thing we'd started out class with, finding where the derivative is 0 or where it fails to exist. But a little bit nicer work on this one. This is a polynomial, so the derivative always exists. There's no chance for it to fail. So we're only really going for that equation, where the derivative is 0. So step 1, differentiate the function. F prime of x is now equal to 6x squared minus 18x plus 12. So in the process, we multiplied by 2 by 3, drop the power down to a 2. Likewise, multiply negative 9 by 2 to get negative 18, power is a 1. If the power is 1 on the function, you just get the coefficient. And this one's a constant, so it went to 0. So there we have it. That's our first derivative. Notice how fast this was compared to our very first problem of the day. Next thing we want to do is, well, we have to set it equal to 0 and solve, but because it's a polynomial equation, it might be a good idea to factor it first. So let's factor out 6, leaving behind x squared minus 3x plus 2. Then this factor is a little bit nicer. This is going to be 6 times two different groups. So we are factoring something with a degree 2. That means we can split x squared as x by x. The positive sign here says all your remittal signs are the same. And the fact that this is negative tells us we have to go minus and minus. Next we factor 2, but it's prime, so all we've got is a 2 and a 1. Next thing we want to do is double check. I'm mostly seeing we're getting a negative 3x. Multiply here to here, that's negative x. Here to here is negative 2x. And we do get our negative 3x. So that's our really fast check right here that the factoring was correct. Any questions to this stage, folks? Finding the derivative and doing this bit of algebra? Okay, let me get these marks off just so it doesn't get too busy to read the notes again. Once you have everything in a nice, fully factored form, just like on the first problem today, this is the step where we'll go and set it equal to 0. Using the yellow highlighting, this means we're finding the critical numbers at this stage. But this is something you could pretty much just read off. X has to be 2, and X has to be 1 to get that 0. If you're a step-by-step person, it doesn't hurt. We needed those step-by-steps last time. Let's say that this implies X minus 2 is 0, or X minus 1 is 0. Notice I didn't do anything with the 6. You can visualize, you could just divide it into both sides, and it's gone. 0 divided by 6 is still just 0. So if you have something that's just a constant, it's not going to give us any solutions. Let me see if I can undo that. Sometimes undoing highlighting is tricky. It's kind of strange. But here's our last step. We're just going to add 2 to both sides on this equation. X equals 2. From here, x would be equal to 1. And we can say these are the critical numbers of f, our original function. Well, we found critical numbers. Next thing we're going to do is analyze the sign of the derivative. We need to know when the sign changes from positive to negative or vice versa. Any questions first, folks, before we go to the next phase of the process? Okay, so here's that next phase. And word of warning, this is kind of tricky because it's the kind of algebra that I think a lot of people don't do very, very often at all. But if you're doing this as a problem in an exam setting, the steps we're about to take are actually very, very essential. For that reasons, these are required steps on both quizzes and exams. Let's mention that just to be specific. These steps are required on both quizzes. Let me spell quizzes correctly first before we move on. And exams. So once we find our critical numbers, we're going to think of them as being cut points in the problem. Let me find just a good color to highlight here. Let's go with, maybe that should work. So next thing we do is we draw out the number line. This is a number line for x. And we begin by putting down the critical numbers on that number line. So we have a cut point at 1, another cut point at 2. Cut points because we're, at this stage, cutting up the real number line into 3 separate regions. One of them is infinitely long in this region. This is a region of finite length. And this is another infinitely long region heading off towards positive infinity in that direction. So next thing we're going to use is fact that this is the derivative right here, but let's just restate it. F prime of x. I'm grabbing it from this line right here where the red dot is. It's 6 times x minus 2 times x minus 1. Because that's the derivative, and because the derivative only goes to 0 in 2 different locations, if you can find the sign of f prime here using only one number, you'll know the sign of the derivative on this entire interval, even though it's infinitely long. And that's because it only hits 0 in those 2 places and nowhere else. So at this stage, we're using test points. Let's come up with a good color. How about this is kind of a lighter green. When you do this on your notes, you want to make your cut points really kind of stand out. Maybe write them in bold, circle them or something. And write your test points a little bit lighter so they don't get kind of misconstrued in your total answer. So they're only used to test the interval and nothing else. 0 is the best test point for this region. There's no reason to work too hard. You're plugging 0 inside here, and we can say f prime at 0. Let me first move that down. Yeah, I was a little worried about that. We're going to need those notes in a moment, but let's hide it for just now. F prime at 0 is going to be equal to, we're just throwing 0 in the line above. So it's 6 times negative 2 times negative 1. And all we care about here is the sign. We don't really worry too much about what the number comes out as. It's positive because it's a negative times a positive. And that means out here, in this entire region, f prime of x is greater than 0. That means the function ought to be increasing until we get to a 1. That's a critical number, so it's neither increasing nor decreasing there. And we need to test out another value. Let's call it 1.5. So we take our next test value, 1.5, throw it into the derivative, and we've got f prime 1.5 is 6 times. Here, this would be a negative 0.5. And here, this would be a positive 0.5. That makes this number negative. 2 positives times a negative. So back to this region. For all numbers between 1 and 2, excluding 1 and 2, f prime of x is now negative. Let me write that slightly better just to center it into the interval. We have in this entire interval between 1 and 2, f prime of x is now negative. So one more test value. I think probably the easiest one would be a 3 in this region. So grab a 3. Calculate f prime at 3, just mostly interested in the sign once again. We're going to get 6 times 1 times 2. And now that's a positive number as well. Plugging 3 here gives us those 2 results. Because we've got positive here, that means this entire interval now has a positive derivative. So we went positive, negative, and positive. Well, we're just about done, folks. This is that required step I was mentioning. If you didn't show this stuff right here, that's not too much of a bother, but you need to show something about the intervals and what the sign of the derivative is. It could be formatted in different ways. This is just the way I typically format it, but some work has to be shown on this direction. Any questions at the moment? Okay, well, continuing on with this, here's finally where the first derivative test comes into play. Or excuse me, that's the first derivative test, and I forgot what the instructions were on this problem. That's not a good test-taking strategy. Find the intervals where f is increasing and where it's decreasing. That's the increasing-decreasing test. Let's go grab that one. These are my own notes, and I forgot how they were organized. Sorry about that. So I want this here just as a temporary screenshot while we analyze the last part of this problem. Part A asked us to find the intervals where the function f is increasing and where it's decreasing. But now in the increasing-decreasing test, we're just using this information. Anywhere we said f prime is bigger than 0 is where the function f is increasing. So we'll start by saying f is increasing on Let's take a look. This interval right here, where we said f prime of x is positive, so it'll be from negative infinity up to 1. Notice we're using open parentheses this time. That's partially because, well, infinity is not a number, so we use a parenthesis to express that. And also, it's not increasing at 1, because at 1, the derivative is 0, not positive. So we use a parenthesis there to express that. Then on this region, it starts increasing again, so we can say union 2 to infinity. Likewise, in this region, it's a negative derivative, so we'll say also, and f is decreasing on 1 to 2. So now we know all the intervals where f increases and intervals where it decreases. Any questions at all, folks, with the conclusion here on part A? Okay, one thing people sometimes put on their chart here, whether it's a number line or just an actual real chart, is once you find that the derivative is positive, not a bad idea to just say INC. As a reminder, increasing, DEC, just as a reminder, it's decreasing there, and INC, just as a reminder, increasing in that interval. Then you're just totally done with the increasing, decreasing test, and all you're writing down here is just the summary of the information you found. Well, now that we have all that, one comment that was made was, part A is not the ends in itself. The whole purpose of part A is to do part B next, to find the local minimum and maximum values of f. That's where we need the first derivative test. Let me see if I can kind of just park it right here. And it's really not too bad. It says here, if f prime changes from positive to negative, you have a local maximum. Let's use this as a kind of exaggerated marker. Here it's positive, it went negative, so we should have a local maximum. But actually, let's change this one up a little bit. Let's use this pen. Another thing you can do on this chart, just to visualize the function, is think of it in these terms. We said right at 1, it's increasing to the left. At 1, it's a critical number, so it rounds off. And then it's decreasing to the right. So your function really looks like this for a local maximum. So we can start by saying, oh, let me not scroll too much. We'll use the zoom out trick. That should work. We'll start by saying right here, f at 1. Let's see, how should we express this? Let's go this way. The local max is f at 1. Let's leave that blank for just a moment and find out what other values we have. So on the next region, it went from decreasing to increasing. Right here, that's where the derivative is 0, so it rounds off, horizontal tangent line. The visual of the function would look about like that. So that means we're looking at a local minimum, and that's what this test is saying. If it changes from negative, here's our negative, to positive, and there's our positive, across the critical number, 2 is the critical number, then f at 2 is a local minimum. So we'll say here, and the local min is f at 2, which is equal to, well, we have to find it. But any questions so far, folks, using up the first derivative test? Okay, and notice this is kind of tricky on the last step. After we've used the first derivative test, the answer is not 1 and 2. It's f of 1 and f of 2, and we have to find those values. But we can't use this. That's the derivative f prime of x. That's why it's so important to put your prime symbols on there, just as a reminder, it's a label for organization. The actual f of x is way up here. Grab that as a temporary screenshot again. Lots of screenshots I've noticed just to make this kind of stuff work. So we go back to the original function, and that does make sense. We're trying to find local maxes and minimums of that original function f. So we have to turn to this one. So first, we're going to plug a 1 into this. 1's nice. That means 1 cubed is just 1. So the first term is just 2. Likewise, minus 9 plus 12 minus 3. So this is negative 7 minus 3, negative 10 plus 12. Looks like a positive 2 altogether. Then next, if we calculate f at 2, that one is a little bit more annoying, but let's write it out. 2 by 2 cubed minus 9 by 2 squared plus 12 by 2 minus 3. That's 2 times 8 on the first term minus 9 times 4 on the second term plus 12 by 2 minus 3. So this is 16. This is also a good reminder. Don't forget calculators on exam. It's mostly for this. 16 minus 36 plus 24 minus 3. Let me know if my arithmetic just goes out of whack on this, but we're nearly there. So 16 minus 36 will give us negative 20. Plus 24 is 44 minus 3. Looks like a 41, unless I messed up somewhere on the arithmetic. But looks like we've got it, folks. The maximum value, the local max, should be 2. And notice how weird this sounds. The local max is 2, and the local min is 41. How do we resolve that? Well, a good idea here with these kinds of problems is something goes wrong, just take a look at a graph to help us out. That's something we can do on the homework and on quizzes. We can't do it on an exam, so think of that as just extra practice when you're studying for an exam. So we're about to go check out this function. I shouldn't have deleted it. Oh, I can't bring it back without Control-Z too much. Okay, what was I saying? We're going to check out these results to see if they're really accurate by graphing the original function. Any questions or comments first? Okay, let's plug this in. Oh, and this is kind of I zoomed in a whole bunch. I'm just going to get a new calculator. That's probably the wise way to proceed. And that is not the right way to spell Desmos. There we go. Okay, let's just throw that one away where we zoomed in a whole bunch. And now finally, f of x equals x cubed minus 9x squared plus 12x minus 3. Might be kind of hard to get a good view rectangle on this, but we'll make it happen. Zoom out a bit. And finally, I think this is a pretty good graph, but I think we can get a better window on this. Let's say for x-axis, we're going from, we should be using the critical numbers, so it should be slightly to the left of 1, slightly to the right of 2. Let's go from 0.5 to 2.5. Then, oh, I messed that up. Let me try again. 0.5 to 2.5. Then for the y-axis values, we're using these outputs. That should have been a 41. Let me fix that. And a 2. So we should have a y-axis that contains those values. Let's go from, oh, not maximized. Geez, I'm in trouble with this keyboard today. We're going to go from 0 to, let's say, 42 or something like that. And that's not quite the boom rectangle I was hoping for. Let me try one more time. So I'm usually a little bit better at Desmos, having some trouble this time. 0 to 50. Let's go from maybe negative 10 to 50. Geez, I'm having a little bit of trouble here. So I have a 1 and a 2. And do I have the function in right? 2x cubed minus 9x squared plus 12x minus 3. No, I don't. I needed a 2 here. That could explain things. Okay, sorry for all the struggles with the technology today, but I think we're about where we need to be on this one. Or are we? 2x cubed minus 9x squared plus 12x minus 3. Looks like it's in there, right? At f of 1, we have a maximum value of 2, which goes right with this one. And here, looks like I might have messed up some arithmetic. Let's see if we go and calculate that a little bit better. So it should have been 2 times 2 cubed minus 9 times 2 squared plus 12 times 2 minus 3. And yeah, that should have came out as a 1. Sorry about the false start on this. I'm not too sure what I messed up here. Looks like that was a, here 40 minus 36. So we're at a 4 minus 3. Yeah, that should have been a 1. That also explains why the graph looks a little bit weird, but I guess that's a good reminder that this is free, readily available. It's a good idea to take advantage of these tools in case there's a simple mistake like the ones I was making. So I think we finally have a good graph. Sure, just trying to get a good viewing window on this once again. So at 1, there's our local max at height 2. At 2, there's our local min at height 1. So plugging this finally all back into our problem. Here's the readout of our graph. So this is y equals f of x. We found a maximum value at 2, and that's it right there. So that's the local max. And likewise, we have a minimum value, a local minimum value at 1, and it's this value right here. Local min. Well, looks like we did it, folks. That's our analysis on the function. And the cool thing about all this is when we get really well practiced, we don't need to see the graph to see if we're on the right track. Just be really careful in the arithmetic, unlike me, and you've got the right values. Well, any last questions or comments before we try out another problem? Okay, so next thing we're going to turn to is, well, as a reminder, section 4.2 is how derivatives affect the shape of a graph. And this is one way. It tells us where the function is increasing and decreasing. If we're just using the first derivative, we get these nice charts for increasing, decreasing. But there's other things we can do. We can calculate, say, a second derivative, and a second derivative also gives us interesting information about the shape of the graph. So here's where we're talking about concavity next. The definitions say, if a graph of f lies above all of its tangent lines on an interval, that graph is concave up in that region. That's an interesting definition in a certain sense because it's, well, extremely hard to visualize just by going with the definition. So let's use this graph for a second time, just to see what they're expressing. I think that should be enough of the function for us. So this will be our kind of guinea pig looking through this definition. So we're looking for a part where it's going to be concave up. Concave up means it takes that shape when you place tangent lines and the graph f lies above its tangent lines. So this is the graph, y equals f of x. If we start putting down tangent lines, say maybe right around here, that's where we had a local minimum. Here's a horizontal tangent line, and the graph is above it. We put another tangent, say, out here. There it goes. I didn't draw it perfectly, but the graph would be above that tangent line. Somewhere out here, there's a switch that occurs. For example, if you put a tangent line maybe right around here, suddenly the graph is not above, it's below the tangent line. There's got to be a transition position somewhere in the middle, but you have to use calculus to really find it. But we can say this now, based on the information we have graphically. If the graph lies above its tangent lines, we're concave up. So it looks like maybe somewhere right around here, it is concave up, because the curve, the one in red here, is above these dashed lines. And vice versa, in this region, somewhere right around here, the curve is below its tangents. So in these regions, it is concave down. So there's some weird transition in the middle, somewhere in this function where it switches in concavity. And that's what we're going to refer to as an inflection point. So if we have a point that's really on the graph, and we'll call it an inflection point, if our graph is also continuous there, and the curve changes from concave upward to concave downward, or vice versa, concave down to concave up. So somewhere out here, probably that location, roughly, is the point of inflection, or just inflection point. So using this definition, we can analyze the shape of the curves and determine when it's concave up, concave down. And notice already, this is kind of a special curve, excuse me. It's increasing in this region right here, but it's concave down as it increases. So although it's increasing, not at a very, very fast rate. Over here, it's also increasing, but it's concave up. And concave up as an increasing function means it's increasing really fast in this region, whereas out here, it's starting to taper down. So that's one kind of bit of information concavity can give us, but also can lead to finding local minimums and local maximums as well. Well, any questions at all, folks, analyzing this graph? Okay, so this is just the introduction to concavity. This is us looking at it visually. It doesn't actually tell us how to calculate anything, how to find the inflection point, how to find the definite interval where it's concave up, concave down. In order to find all of those things, we have to go here to the concavity test. Let's put down a really temporary screenshot actually before we look at that test. It's going to be this as a screenshot. So just a temporary side-by-side comparison, but this is a good one for that kind of comparison. So the concavity test says, if your second derivative is positive for all x in some interval I, then your graph is concave upward. So that's a remarkable thing. Concave upward is either your tangent, your curve lies above all its tangents. That's something you have to visually inspect, or it's just where the second derivative is positive. That's something we can calculate and find regions exactly. Also, the second derivative is negative, and the graph is concave downward. So that's going to help us find where the inflection points are. It's not too different from what's going on here in the first derivative test. And also, it's not too different from, let me grab one more screenshot, the increasing decreasing test. Let me dump that down below just temporarily as well. The increasing decreasing test says if your first derivative is positive on an interval that's increasing, that sounds an awful lot like saying if your second derivative is positive on an interval I, then it's concave up. Likewise, first derivative negative means you're decreasing. Second derivative negative means you're concave down. And the reason I'm doing this side-by-side comparison is because example 1 and example 2 are extremely similar. It's almost like the same problem. The only difference is you're going to a higher order derivative in example 2, only because it's asking about concavity. That's really the only difference. And maybe the second difference is in example 2, we're not looking for a local max, local min. Instead, the related thing is we're finding points of inflection. Once again, everything is extremely similar here as a process. All we have to do is just get to cranking out derivatives. I think we might have enough time to get through example 2, so let's give it a try. Any questions whatsoever before we launch into this one? Okay, let's give this a good go. Our problem in example 1 was just a polynomial, so the derivative was straightforward. But this is not going to be the most friendly kind of derivative. We need a chain rule to get through this one. So let me just start by copying down the function. F of x is natural log x power 4 plus 27. In this configuration, the inner function is x power 4 plus 27. So that's function 2, inner. Function 1 is going to be natural log x. So we'll call this one function 1, outer. What makes natural log the outer function is x power 4 plus 27 is going inside of it to form the overall function f of x. Next, if you're differentiating natural log x, that was just our last section, 3.7, we get a 1 over x. So here's how the chain rule is going to work. Let's actually color code this one. This one is maybe not. Let's keep these color codings up here and not get too carried away. That would be too much color coding. F prime of x is going to first be the derivative of the natural logarithm, which means we're using that expression there for its derivative. But in place of x, put in a big placeholder. So it goes 1 over a parenthesis, there's the placeholder. Then we multiply by the derivative of something. That's the chain rule part. So once we use up this, we took care of derivative 1, the outer function. Next, we take the inner parts, x power 4 plus 27, and just dump them into both placeholders. It's always the same process, but like we said at the start of class, the type of function makes it feel different. So take a look at the last example where we were doing an exponential versus what we're doing here with the logarithms. Same kind of process, but just it feels different until you get a lot of practice with it. Well, this derivative is almost done. X power 4 plus 27 stays below. We differentiate this and multiply it into the numerator, so we'll get 4x cubed. And we've got it, folks. That's our first derivative. But the problem says find intervals where f is concave up and concave down, which just guarantees we're using the concavity test, which means we now need a higher order derivative. We go now to the second derivative. So one more step. Notice in the first derivative here, we're just using chain rule. Now in the second derivative, there's no logarithm anymore. This is just an ordinary quotient rule this time. So here's f double prime of x. Let's write this one out carefully. Kind of a review problem at this point with quotient rule. It will be the derivative of the numerator. Copy the denominator and multiply. Subtract for quotient rule and then copy the numerator. Multiply by the derivative of the denominator. And then finally take all of that stuff, divide by the denominator, squared. So the denominator is just going to stay like this for all of time, but now we need to simplify the numerator as much as feasibly possible. Reason for that is, if we're using the concavity test, that means we have to go to a real number line, find critical numbers, so we can actually solve these two inequalities in blue and in green up here. So it takes a little bit of work to get through this and simplify it all the way down, but it's worth the effort, or else solving the equation is going to be like torture. So first we differentiate this. That'll be a 12x squared. Multiplying x power 4 plus 27 minus 4x cubed. Then differentiate this one next. That's going to be 4x cubed. Then the denominator is, again, just being copied. X power 4 plus 27 squared. Next step we need to take is distribute 12x squared into that group. We'll get 12x power 6 plus, and I think I need a calculator for this one, 12 by 27 is coming up next. That is a 324. So we'll get 324x squared. One more distribution. This is going to be -4 by -4 for -16. X cubed times x cubed. We'd add up the powers to get x power 6. Slowly but surely we're getting there. X power 4 plus 27 squared. This is one of those things where it seems to just keep going. Now we have like terms in the numerator. So we can call this 324 x squared. Then it's 12x power 6 minus 16x power 6, or a negative 4 x power 6. That's starting to look a lot better. But now that we're in this stage, it's a good idea to simplify even more. That's almost a weird statement to say, but remember, we're going to set this equal to 0 and solve. That means simplification in this context means factor as much as you can. Let's test if we can divide 324 by 4. That seems totally plausible. Well, I need the number anyway, so let's just do it here. And I didn't want the console. I need a new keyboard. I think I keep miskeying stuff. So this is, in the calculator, 324 divided by 4. We get a nice 81. That means we can factor out 4x squared from both of these terms. So here's 4x squared factored out. 4 divides the 324, leaving 81, and now x squared's gone. Here, we're dividing out 4x squared, and that's leaving x to the power of 4. Down below, x power 4 plus 27 squared. So still getting there. These are one of those kinds of problems where they are pretty long. So that's another kind of skill that we're practicing, just surviving a long problem. Where the red dot is right now, we can factor that even further. We'll go 4x squared. The formula we're going to use over here, same kind of formula we've seen whenever we're dealing with conjugates. It's a squared minus b squared. Factors immediately as a plus b times an a minus b, our difference of squares formula. So this formula here says, where you see an 81, write in a 9 plus x squared. Next, in place of 81, go 9, but now minus x squared. And it has to be x squared because when we go to FOIL, x squared by x squared gets us back to x power 4. It gets kind of tedious copying down that denominator every single time. I have to admit that to you, but it's well worth the work ethic to copy it down, lest we forget it even was part of the problem. So this is looking good. 4x squared can't be factored. That can't be factored either. That's a sum of squares. Put down a quick note. Not factorable. That's not totally true. You could use complex numbers to factor that, square roots of -1, but we're only using real numbers in this calculus, so that's why we're saying not factorable. But that one, where the red dot is currently, it does factor. We'll use the difference of squares formula again on that one. So this is finally our last step, I promise. We have 4x squared, 9 plus x squared. Factor this one as 3 plus x, 3 minus x. Divide the whole thing by x power 4 plus 27 squared. And this is our second derivative in its most simplified format. Any questions at all, folks, calculating that total second derivative? I need to learn to write smaller. That took up quite a bit of the page. Okay, let's get back on track with our ultimate goal here. It's to use the concavity test. Concavity test relies on the sign of the second derivative, so that's why we calculated this thing right here. But to solve those two inequalities, we need to do something else further. We now need to solve f double prime of x equals 0. And I don't think I'll fit that on this page, so let's just say this continues. Scroll down to about that spot. Right here by the red dot, that is the second derivative of x. So we're taking 4x squared, 9 plus x squared, 3 plus x, 3 minus x, x power 4 plus 27 squared. Let's also label this just as a reminder. This is now the second derivative of f. And now we set it equal to 0 with the hopes of solving those two inequalities in the concavity test. Solving this set to 0 is not as bad as it looks. First of all, the denominator has no influence. You can visualize this happening. Multiply both sides by the denominator, it gets cleared out on the left, and the 0 just annihilates it on the right-hand side. So that part's gone, and your next step is that 4x squared, 9 plus x squared, 3 plus x, 3 minus x, is set equal to 0. So clearing the denominators just means the only way this equation is ever true, every single time you have a fraction, is if the numerator itself is 0. Now we have, what, 4 different factors all set equal to 0. This is the third time we've used this property. The only way this equation is true is if 4x squared equals 0, or this one, 9 plus x squared is 0, or just keep on going down the line, 3 plus x is 0, or 3 minus x is 0. So we have 4 different equations, and they're not too bad to solve. On this very first one, x has to be 0. That's the only way to make that true. Even if you divide by 4, you'd have 0 is equal to x squared. Square rooting it just would say square root of 0 is 0. So that's the only way to make this equation true. That equation right here is a little bit special. Remember, this is the one that didn't factor, and this one also has no solution. Expanding on that a little bit further, imagine what you would do if you tried to get a solution. You would subtract 9 from both sides. You would take square roots of both sides. And that's where we get an issue. This is a complex number. We only are going for real number solutions. We would say this x is plus or minus 3, that's the square root of 9 part, and I is the square root of negative 1 part. So we just say altogether no solution, because that is not a real number. We just move over to the next. Subtract 3 from both sides. And on the next one, add x to both sides, and x equals 3. So we can say these are the critical numbers, which means we're about ready to use the concavity test. Really, the major work here was just getting the second derivative, setting it to 0, and finding those critical numbers. That took almost all of the time, but the last steps is just to summarize. However, I think I'd have to really rush to finish off this problem. This might be a good one to come back. We'll mention what we did here on Monday, not necessarily redoing it all, that's a lot of work. And then take up on the new part, using this information to get the intervals where it's concave up, concave down, and inflection point. So this will be our stopping point for today's class. Any last questions or comments then before we call it a day? Okay, well, have a great weekend, folks. I guess tomorrow is Halloween, so have a safe Halloween as well. I'll see you all in Monday's class. Take care.